Today I'll be talking about a phenomenal paper called The Perceptron, written by Rosenblatt. It's a research paper that talks about this module that has been designed to replicate how the human mind works and how our brain activity works. It's a model that mimics our thinking and our recognition patterns. So for example, if you saw a picture of your friend on Instagram, this is a picture that you have never ever seen before of your friend, but you see this picture and you immediately recognize that, oh, this is my friend Angela. Yeah, that's something really interesting and fascinating that our brain does that machines can't or couldn't do for the longest time. And Frank Rosenblatt came up with the first and simplest representation of the neural network, and he called it the perceptron. The idea of this perceptron is that it can create a classification of patterns in linearly separable states. So the idea of a linearly separable state can be seen in separating, like creating an input space where if you put in two objects of different characteristics in this input space, you could actually separate the input space such that the two objects are in their own isolated spaces. So for instance, this is a glass of water. If I put a metallic coin here and I put a paper coin here, what's going to happen? The metallic coin is probably going to sink to the bottom and the paper coin is probably going to float. Now this is just a very basic idea of what linear separation looks like. However, a logical representation of this linear separability can be seen in logic of and. I'm sure you might be familiar with AND operations or operations, etc. So let's look at an example. Now I'm sure we're all familiar with AND operation, but I'll just go over it just so that everything is extra clear. So with the AND operation, you know, there is the x and y, and then there is the AND operation for the x and y. So if x is 1 and y is 1, the AND operation is going to be 1. If x is 1 and y is 0, then the AND operation is going to also be 1. If x is 0 and y is 1, then the AND operation is going to be 1. But if x is 0 and y is 0, then the AND operation is going to be 0. Now let us look at this as a graph. In the graph, we see, you know, this is the y-axis and this is the x-axis. So if x is y and 1 is y, so x is y and y is y. You see here is 1. And if x is 1 and y is 0, here is 1. Remember, 1, 1. If y is 1 and x is 0, so y is 1 and x is 0, 1 is over here. If x is 0 and y is 0. So yeah, after creating this table, after representing this AND operation in this table, you can see that we can easily separate the two states. In one state, you can see all the ones are in this area. All the ones are above the demarcation line, and all the zeros, in this case there's only 1 0, so all the zeros are in this demarcation line. And you know, this is an example, or this is the premise of the perceptron, basically creating a model for us to, you know, represent this classification patterns. So now this is the basic premise of the perceptron. But you know, right now, that's my cat. However, the perceptron also recognizes that human behavior is quite complex. And right now what we have here is just a Boolean sequence of, you know, classification systems. So the idea of a perceptron, according to this book, which was written in 1958, is to replicate the biological functionalities and the biological properties in the human neural network without the deep nuances. In order to create a perceptron, basically the perceptron was a whole new idea from other existing systems at that time in 1958. So in order to create these entirely new principles, he highlighted some flaws in the previous principle. So for instance, one of them was lack of equipotentiality. Equipotentiality is the idea that components within a system have the same potential. For instance, in neuroscience, equipotentiality can be observed in when a cell within our body dies, because it originally had the same potential with other cells that are similar to that cell. Then if cell A dies, then cell B can take over the behaviors and take over the functions of cell A. And the whole idea of equipotentiality deals with the fact that functionality is not localized. So every cell has the same potential, meaning that they have similar functionalities, or they have full functionalities that is expected of them, if that makes sense. So the second is lack of neuroeconomics. Lack of neuroeconomics is a method of implementing reward or punishment within a system. So imagine you went to school and you studied and studied and studied, and at the end of the year you just came back home. There is no GPA, there is no, exams to gauge your success or failure. Then studying would almost seem meaningless. Now that's the idea of neuroeconomics that Rosenblatt was trying to implement and trying to demonstrate as a flaw in previous models. And this was something that he was very intentional about implementing in the perceptron, and we'll discuss this in further depth in later parts of this video. The third thing is excessive specificity of connections. Now, this characteristic is a function or is an output of these two characteristics. So this is the idea that because the systems isn't independent, the creator of the system has to be extra intentional in micromanaging how the connections are made. So, because you're over specifying all the interactions between, the system and between the association cells, then it makes it so much more difficult. And, that's a flaw that he recognized. So the fourth flaw is postulations of features that lacks correlation with neurological processes. Basically, what this means is, because the goal of the perceptron is to create a system that mimics our human brain and that mimics our biological neuron, then that system needs to rely on properties and behaviors that are similar to our brains and our thought process, if that makes sense. So that was a gap that he noticed in previous systems that he was intentional about fixing in the perceptron. Now, the author started the book by mentioning a few questions that could help us understand the process of perceptual recognition. Remember, perceptual recognition is the way our human brain works on recognizing patterns and identifying characteristics in different objects. So the first question is, how does human biology perceive or sense information in the physical world? It's a very important question. Like, how do we actually see? How do we actually know? These are questions that we don't necessarily have the answers to, but the research tries to dig deep into providing a response for it. The second question is, in what form is the information stored? Very valuable, because when you find out how the information is stored, then you're able to efficiently recall that information, and that could feed into the answer that we might be hoping for how the human biology is able to perceive things in the world. Now, the third question is, how does this information influence future recognition patterns? Very important. The book, however, focuses on question 2 and question 3. To answer both of these questions, there are two main theorists. The first theorists, I would call them decoded memory theorists. And then the second theorists, I will call them the empirical theorists. Decoded theorists, now for each of these questions, there are two hypotheses based on those two theorists. So the first hypothesis for the question, what form is information stored? Now, decoded memory theorists, they believe that information is stored as a code, encoded representation of stimuli. And that stimuli is then mapped with a response. And then the second theorists, the empirical theorists, they believe that information is actually never stored. And every time we experience a stimuli, we create new connections for that stimuli. These are two very different approaches to these two questions. I just want you to take a second to think about what theory you think you support or which one you believe makes more sense compared to the other one. Now, for the third question, how does information influence recognition patterns? Now, for the first hypothesis, which believes that information is stored as coded representation of data, which is then mapped to our response, it believes that the hypothesis regarding that is that when future patterns or when future stimuli is experienced, the human brain will search through the history of stimuli that has been saved in coded representations and then basically regurgitates the appropriate response based on the history of that individual. While the second theory, the second hypothesis is that since information is never stored, there is never a need to go back to the history of a person's experiences. And rather than going through the history of a person's experiences, we just, create new connections and create a new response. So think about that again. Which one do you think makes more sense? Now, based on the limitations of existing or previous models at the time, this new model is based on new assumptions for the perceptron. So the first assumption is uniqueness. It is believed that every living organism has a unique neural network. And I think that allows us to create this artificial neural network in such a way that we can accommodate for the nuances that makes it different from the biological system. Then plasticity. Basically, the neurons within the neural network are able to evolve over time. So for instance, the state at which the perceptron starts is different from the state at which the perceptron exists after it has completed its processing. Obviously, because we expect some learning to occur. Just like the way I was so different before I read this book and the way I'm different after I read this book, humans evolve. So we're expecting that the perceptron is also able to evolve. The third is similarity in similar stimuli outputs. So for instance, similar stimuli will present similar responses. I'll give an example. If someone touches you with hot water, you're going to flinch. That's just your natural reaction. Basically, in this case, the stimuli is the heat, and the flinching is your response to the heat. Now, if someone touches you with not hot water this time, but hot oil, what are you going to do? You're probably going to flinch as well. Remember, the stimuli is very similar. Hot water, hot oil, they are similar in the sense that their main characteristic is heat. And because they are similar, you give basically a similar response, which is you flinching. Maybe you might flinch a little bit more because oil is hotter than water. But either ways, you still flinch. That is a similarity in response. Another example is if someone was to give you a compliment, like, oh, I really love your hair today. You're going to smile. The compliment is the stimuli, the positive affirmation is the stimuli, and your smile is your response. And if someone says, oh, I really like your hair, that's like, makes you smile. And on the other hand, if someone says, oh, hi, I really love your dress, that's also a similar stimuli that could also make you smile. So you see how this behavior is trying to be mimicked in the perceptron. So now the fourth characteristic, the fourth assumption is reinforcement. Reinforcement goes back to neuroeconomics, the ability to give positive or negative signals to discourage or encourage connections. So for instance, in the previous example, I talked about smiling when someone compliments you. That's a positive reinforcement, and that gives the person the signal that, oh, you actually like compliments. And maybe if the person saw you again tomorrow, the person wants to give you another compliment because your smile encouraged that behavior. Now, on the other hand, if for the flinching action where someone touched you with hot water or hot oil and you flinch, the flinching is a negative reinforcement because it signals fear or frustration or pain. And the person who did that will not want to inflict that negative reaction from you. Hopefully, they don't want to inflict that on you again. So the next time they see you, they'll be hesitant to pour hot water on your skin. So in the perceptron, Rosenblatt's paper, he demonstrates the characteristics of a perceptron using a photoperceptron, basically a perceptron that is designed to identify visual data. But before I explain the characteristics of that perceptron, I just want to define a particular component that will be very important in explaining the system in which it exists in. So the first is the S points. The S points represents impulses. The S points represents impulses that are transferred into the A units and within the system. So the A units can be described as association cells that receive S points. And this A unit has a value or can be described as a weight. So the strength of the A unit is determined by its weight, and its weight is determined by the S points. This S points influences the A unit's weight by either being positive S points or negative S points. The positive S points are the S points that act as positive reinforcements for the A unit and positive reinforcements for the stimuli that it receives or the stimuli that it represents, right? And another name for the positive reinforcements is excitatory connections, because excitatory connections. While the negative reinforcements are called inhibitory connections. So excitatory connections strengthen the connections of the A units within the A sets, and inhibitory weaken the connections. So yeah, this is basically the relationship between the S points and the A units. Well, an A set is a collection of A units. That's just what it is, a collection of A units. Now we also have something called a source set and a complement. A source set is a collection of A units. Basically, a source set is an A set which produces a response, while a complement are A units, or a complement is an A set that is not part of a source set. So if this is the source set, then the complement is this other dots. In some perceptron models, the stimuli triggers the perceptron in an all or nothing fashion. So either every part of the perceptron is fired up, or no part of the perceptron is fired up. But in this model, the perceptron is fired up in accordance to the weight of the stimuli. So it measures the weight of the stimuli, and then based on the weight of the stimuli, that's the extent to which the perceptron is fired up. So for the perceptron to exist and function, there are different systems in which the perceptron can exist in. Actually, 3 different systems. So the first system is the alpha system, the second is the beta system, and the third is the gamma system. So in the alpha system, the reinforcement, I think the difference, like the primary difference in all the system is the method in which the reinforcements are calculated and given to all active or inactive units. An active unit is a unit that fires up after an iteration, like after a round, while an inactive unit is a unit that doesn't fire up. So for instance, in the previous section, like previously, I had talked about a source set, and a source set, I mentioned it to be a collection of A units in which those A units respond to the stimuli. So that's basically what I mean as fired up. So in this case, an active unit is an active A unit is an A unit that exists in the source set, while an inactive A unit is an A unit that exists in the complicit set. So yeah, these systems, we have the alpha, the beta, and the gamma. So in the alpha system, all A units will get a +1 in their value. +1 is hypothetical because it could be +30, it can be +10, it can be plus whatever, but 1 just represents the points that is added to their value in this case. So in the alpha units, all active A units would get an additional value of +1 hypothetically, and there is no upper bound. It's just recognized that if you're an active unit that got triggered, then you get a +1. While in the beta units, there is no exact value that is given to all active units. What is given is there is a total additional gain, and that total additional gain is split amongst all the active units and divided and shared to them evenly. So for instance, I said here total over n, where n represents the number of active units and total represents the total gain. So if, for instance, the total gain is 10 and there are 100 A units, then each A unit would get 0.1. And if there are 1000 A units, then each unit will get 0.01. So that's basically what the distribution of reinforcement looks like in the beta system. And in the gamma system, it has a more interesting and involved way of giving reinforcement. So first of all, it makes sure that every active unit gets a +1, but it also makes sure that every inactive unit gets a -1. So if you're an inactive unit, you get like punished, and then if you're active, then you get an additional gain. So analyzing the metrics for each system, one of the metrics is the total gain per reinforcement. So the total gain for each reiteration. In the alpha units, in the alpha system, the total gain for a particular reinforcement period is basically just the total number of active units in that round, since every active unit receives one value, like one additional point. In the beta system, the total gain per reinforcement is just the total. It's a constant value of the total. It doesn't change. Once you've predetermined what that total is going to be, then it just stays that way and gets redistributed around all the active units. For the gamma, the total additional gain for a gamma system per reinforcement is going to be 0, because when the active unit gets 1, the inactive unit gets -1, and if you add these two together, you get 0. So this system stays balanced. On the other hand, if you try to examine the mean of the active system would increase after every iteration. It will increase after every reinforcement round, while the mean of the beta increases with time, because since the total is constant and it just increases, it just increases with time. While for the gamma, it's actually just never increases, it's constant at 0. So these are very interesting things to consider when designing your system in which you want your perceptrons to run. I'm curious which one you think is the most reasonable system to use. During the process of learning in the perceptron, we rely on the predetermined rules in the system. So the predetermined rules in the system are either the alpha, the beta, or the gamma rules. So rely on those predetermined rules to check the strength of the stimuli with a particular response. And the strength of that stimuli would be determined by the inhibitory connections and the excitatory connections. So what those two connections do is they help to gauge whether an A unit is going to fire up. And remember, the A unit is one of the components in the source set. We're going to represent this in a mathematical function called the base probability. The base probability is a binomial probability where this section of the base probability is the probability of getting exactly E excitatory connections out of X possible excitatory connections. And this part is the probability of getting exactly I inhibitory connections out of Y total inhibitory connections. Now, why is this relevant? It's relevant because every A unit can only be fired up when the amount of inhibitory and excitatory connections match up to the threshold. So now, assuming that the threshold is equal to 50, for a threshold value to be equal to 50, it means that whatever we get in whatever number of excitatory connections and whatever number of inhibitory connections will sum up to be either greater than or equal to 50. So if we have 500 connections, 500 inhibitory connections, then we must have at least 550 connections, so that by the time we subtract these two values, we get a value that is greater than or equal to 50. So because of that idea of determining the probability that a unit is going to fire up, that's what led to the creation of this base function, and that's why this base function is relevant. So yes, the simple idea of what this probability does is that it helps us to find out the probability that we would get exactly. So what is the probability that we get exactly E excitatory connections and I inhibitory connections? And there are quite a few things that would affect the sensitivity of the A units. So for instance, if the threshold value is very, very high, so if the threshold value is maybe equals to 5,000, then that's very, very high, and it could make the A units to be less sensitive, because now for this to be fired up, we need E to also be very, very high. Another thing that could make the A units to be less sensitive and less likely to fire up is if the inhibitory connections are also very high. So if the inhibitory connections are very high, then even if we have a threshold value of maybe E equals to 100, if I is very, very, very high, that's if the number of inhibitory connections is very, very high, then it will also be difficult for that A units to be fired up. And look at it realistically, because if the amount of inhibitory connections is very high, then that's basically the system sending a signal to that A units that, hey, you're not relevant, so you don't need to be fired up. So obviously that's going to affect whether that A unit fires up or not. On the other hand, an A unit could be too sensitive in the sense that it fires up way too frequently, and this would happen if the threshold value is way too low. So if the threshold value is way too low, then there is very low barrier to entry. And this could be problematic because it means that the A unit generalizes too much. Meaning that imagine you have the same reaction, the same flinching reaction when hot water touches you, the same flinching reaction when cold water touches you, the same flinching reaction when somebody compliments you. Like you have the same reaction for everything. It means that your response generalizes the effects of a stimuli way too much. And on the other hand, if your A unit is not sensitive enough, that is, the instance where the threshold value is very high and the inhibitory connection is very high, it means that your A unit discriminates a little bit too much as well. So because it discriminates a little bit too much, it's more selective stimuli, and that's also a problem. So, we have on the far end too much discrimination, and then we have on the other far end too much generalization. So we are looking for like a balance point in the middle where we're able to, discriminate efficiently but also generalize efficiently as well. And then we have P of R, which is another probability. So this is the probability that A unit responds to a single stimulus. This is derived from taking a summation of all the inhibitory connections and the excitatory connections such that E minus I is greater than or equal to the threshold. Depending on how high or how low this threshold value is, it affects the sensitivity of the A unit. But something else that is so relevant to discuss is the fact that our estimation of P of R can also be influenced by the number of connections that the system has. So basically, when we have a higher number of E and a higher number of I, we're able to observe smoother representations of P of R. And the reason that this is the case is due to something called the law of large numbers. The law of large numbers states that if you repeat a random experiment many times, the average results, which is basically the sample mean, will get closer and closer to the expected value. So now imagine this as a coin toss problem. So in a coin toss problem, we know that the probability of getting a head versus the probability of getting a tail is 0.5. However, if you toss the coin 5 times, or if you toss the coin 10 times, there is a likelihood that you probably wouldn't get an even split between heads and tails. You probably get something like 7 heads and 2 tails, or something quite uneven if you were to flip the coin 10 times. However, if you flip the coin like 100 times or 1,000 times or 10,000 times, because of the sheer volume of experiments that you've performed, then you're able to get a smoother and close to and a value that is close to the expected value. So mathematically, we know that the probability of getting heads versus tail is 0.5, but practically, when you're carrying out this experiment, that's when the law of large numbers comes into play. And that's also something that happens when you're dealing with inhibitory and excitatory connections, and when we're trying to get the probability of R, and the probability of R is the probability that A unit fires up when the threshold has been bypassed. Assuming we have a stimuli, let's call it stimuli 1, and another stimuli called stimuli 2, we are going to discuss a concept called common activation. So common activation can be seen in an overlap between L and G. Now, L is the portion of S points that lit up during the learning process of S1, but not during the learning process of S2. On the other hand, G is the portion of S points that lit up during the learning process of S2, but not during the learning process of S1. What does this tell us? It kind of creates like a demarcation between how we respond to one stimuli versus how we respond to the other stimuli. And of course, L would have a couple of excitatory and inhibitory connections, and S2 would have a couple of excitatory and inhibitory connections as well. And you know, all of these, when the excitatory and inhibitory connections are greater than the threshold, then that allows the activation of the A units within the S1 simulation learning process and the S2 simulation learning process. So yes, there is now this probability called P of C, which is the probability of common activation. If P of C is high, then it basically communicates to us or signals to us that the stimuli in S1 is very similar to the stimuli in S2, because there is a high probability that the S points that gets triggered has a large overlap with the S points that get triggered in G. So for instance, earlier I had given an example of someone flinching when hot water is poured on them and also flinching when cold water is poured on them. Those are similar stimuli that lit up the same areas in our brain and caused a very similar reaction response. So that's also, you know, is a practical observation of what happens when there is a large overlap between L and G, and also a similarity in the stimuli. But there could also be a contradiction, and this contradiction is what helps us to understand the generalizability of our perceptron. So if P of C is high, but these two stimuli are not similar, then that tells us that, you know, our model generalizes too much. And if P of C is low, but our stimulus S1 and S2 are very similar, then that tells us that our model discriminates too much, just as I had explained. So there are two ways to observe the efficiency of our model, and both of these evaluation methods are quite similar because they use the trial and error method. In the first method, we present our model with a set of stimuli. To test and evaluate the success of our model, we give it the exact same stimuli and then check whether it gives us the exact same response. So for the first trial and error method, we basically repeat our inputs. Now for the second trial and error method, we don't repeat the inputs, but we do give similar inputs so that to check whether the model is able to gauge the response successfully. So for instance, this is what we give during the training process. But for the testing process, instead of giving S1, we give a stimuli that is similar to S1 called S11. And then we expect that instead of the response to be R1, it gives a similar response which is R11. Do you understand? So there's just like a slight difference in maybe the orientation, the color, just a slight difference in the class that is being shared with the perceptron, and just seeing whether it can generalize its outputs. So for the first trial and method error, we are measuring something called P of R, which is the probability of correct response. It makes sense because since we are checking the probability of a correct response, then we are comparing the exact same stimuli and the exact same output during our testing. And in the second trial and error method, we use something called P of G, which is the probability of correct generalization. And that's why instead of giving the exact same stimuli, we give a similar stimuli, but we expect it to produce a similar response. So digging deeper into P of G, we can actually calculate P of G mathematically using the following formula. So P of N R greater than 0 multiplied by Z. N of AR is the number of A units that become activated. So what this portion is saying is, what's the probability that at least one A unit is fired up? and Z accounts for the signal to noise ratio. So this portion tells us the probability that a correct response is activated at all. And then this portion tells us that if the correct response is activated, but also if the incorrect response is also activated within the same round for the simulation, what's the probability that the correct one will win given the strength of the connections? And for the noise, we have 4 coefficients here. Coefficient 1, coefficient 2, coefficient 3, and coefficient 4. But we also have a value called n of SR, and n of SR basically represents the number of stimuli used in the training. Understanding all of this is what moves our evaluation from a unit level to a system level analysis. You know, for the unit level, we are checking if a unit is even triggered at all. So is a unit even triggered? That's the system level. And to check if a unit is triggered, we make a comparison between the number of excitatory connections and the number of inhibitory connections. But on the system level, which is this, we are checking the probability of correct classification. And correct classification is done through correct generalization, which is implemented in this for probability. So now we're going to dig deeper to observe P of R and P of G in randomized and ideal environments, and this is considered to be the simplest state for the perceptron to operate in. A few things to consider is because this is a randomized experiment, we expect that P of G would equal 0.5 because it's randomized, so it has basically the same probability as flipping a coin. While we also expect the noise to signal ratio Z to also be equal to 0, because if it's an ideal environment, then there is no noise, so Z will basically be 0/negligible. But this also gives us the opportunity to observe the constants in relation to how it produces P of R, which is the probability of a correct response. So C1 is the baseline penalty, and since C1 is 0, it basically tells us that active cells are not being punished. And so yeah, it's 0, it's a constant 0. C2 is called the credit noise. So P of A is the probability that a cell is active. So here we are doing P of A multiplied by n, and n is the number of cells in general in a subset. So this tells us the credit noise, which is how much the inactive cells interfere with the performance of the active cells. And this is in the alpha system because there isn't a normalized way to gauge performance and to gauge like addition of values in those cells. C3 is the overlap noise. When there is high overlap and there is like a lot of connectivity and interactions between the cells, then because it's a false sense of reinforcement among the cells, so the cells will start to reinforce each other, which could lead to something called overlap noise. And that's why that's a criteria when discussing how this affects the probability of a correct response. And then C of R is going to be equal to 0. C of R basically represents other forms of noise. Now we just finished explaining the coefficients in the alpha system, and the coefficients in the beta system are very, very similar with the coefficients in the alpha system, except that in the beta system, C of 3, like the third coefficient, scales with all these parameters, making it significantly more sensitive and significantly more unstable. Now remember the characteristics of the beta system. The beta system states that there is one additional gain. So assuming that this is the additional gain, this box right here is the additional gain, and then this additional gain is split and distributed to all the active cells. Now, this seems reasonable, or at least it seemed reasonable when I first read about it, but think about it more deeply. Meaning that with every round, the same additional gain is split into multiple active cells. So it makes the additional gain for the A units to be even smaller and even less significant. And because the number of active cells could increase, decrease, it makes it super unstable because there is no definite growth pattern, if that makes sense. And this also allows us to go into something called the mean discrimination and the sum discrimination methods of evaluating whether an A unit would fire up or not. So with every A unit, there is a weight, right? And in every subset, there is multiple A units. So if you want to determine if a subset fires up to a particular response, there are different ways to determine that. And those two ways are either through summation or through mean. So you could have a threshold value that recognizes summation. That is when you add the value of all the A units in that subset. Does the sum of all those values give you the desired threshold and more? And then you could also have another threshold that is sensitive to mean, that is designed for mean. So if you take all the weights within that unit and you take the mean of that weight, does it allow the subsets to bypass the threshold and give the desired response? These are very, very important things to consider. And before we talk about it, I'd like for you to just take a second to think about which system do you think is the most stable and the most reliable system. So to analyze the efficiency of this sum discrimination and mean discrimination method, it's going to be helpful for us to break it down based on the systems in which these discrimination methods would exist. So for instance, with the alpha system, with the sum discrimination, it actually doesn't perform as well. It's very, very unstable, and you can see that from the figures. And with the mean system is, more stable, reasonably stable. Now with the better system, both the sum and the mean are unstable. Both the mean discrimination and the sum discrimination methods didn't yield satisfactory results. And then for the gamma system, is insensitive to what discrimination method you choose. The gamma system doesn't need a particular discrimination method to decide or to produce satisfactory results, which is a good thing because it means that it makes it unbiased. So in the systems that we just explained with the class similarities, we're also going to discuss the coefficients of the systems. For the C1, this is the signal gap. So what's basically the difference between the probability of similar classes and the probability of non-similar classes? So that's how C1 is calculated. And C2 is calculated by the finite sample offset. And this becomes negligible. As the training gets larger and larger, this coefficient becomes negligible. C3 is the sum of variance terms. This includes the heterogeneity of the A units. This includes the overlap on the weights. So in order to further improve the performance of the model, we can use two methods to improve this. And this could be, the first method is through binary coding, and the second method is through bivalent systems. In binary coding, this is where we identify a finite number of characteristics and represent that finite number of characteristics in codes or in binary bits. And each binary bit represents whether or not that finite characteristic exists. So for instance, if I was to represent a human as a binary code of whether that human has eyes, head, and tail. Of course, the human have an eyes. Do humans have eyes? Yes, humans have eyes. So this is going to give a value of 1. Do humans have a head? Yes, the humans have head. Do humans have a tail? No, humans don't have tails. So the binary code of a human based on these three characteristics is going to be 110. So this is what, obviously this is a very, very, very simple explanation, but it's also what binary coding means and how it is used to make the systems more efficient. So now imagine we have stimuli, like up to 1000 stimuli. If you can find a way to represent those stimuli in a finite number of characteristics, then it reduces the mapping from 1000 stimuli to 1000 mapped responses, and it reduces that into just maybe 3 characteristics. The second is the bivalent system. So this system permits positive and negative reinforcements on active cells. Previously, we had talked about negative reinforcements on inactive cells, but now in this bivalent system, we talk about negative reinforcement on active cells as well. So active cells can also be penalized within this system, and this is helpful because not every active cell is active in a way that makes sense in alignment with what we want from the perceptron or what we want from the model. So, it helps us to streamline the judgment of the A units within the cells. So for instance, if a cell actually fires up but its output isn't desired, then we could penalize that A unit such that we inform it that its judgment isn't what we want, and because of that we're able to weaken the connection. So that's definitely helpful in reducing biases for wrong responses due to a response having a high frequency. And when in the previous example we talked about noise, this helps to prevent a noisy module, because we now know that just because an A unit has a high frequency doesn't mean that we could trust its response. We've come to the end of discussing this perceptron, but there is also something very important to mention, which basically demonstrates a flaw in the perceptron. So remember, we talked about how the goal of the perceptron is to implement linear separability of two classes, and then we discussed how this linear separability can be achieved through the different systems, different metrics, the different discrimination methods between the cells and between the A units and within the stimuli and its responses. Now, even though this research paper was extremely helpful, it actually had a flaw. And the flaw was that the perceptron, even though it could establish linear separability in a lot of different classes, it failed to achieve linear separability in the XOR logic. And I'm going to demonstrate the XOR logic right now and how that linear separability was failed. So in the XOR logic, we have X here and we have Y, and we have XOR X and Y, X and R. So if X is 1 and Y is 1, then XOR is going to be 0. If X is 1 and Y is 0, then XOR is going to be 1. If X is 0 and Y is 1, then XOR is going to be 1. If X is 0 and Y is 0, then XOR is going to be 0. Now, if you can remember earlier, we did an experiment similar with this with the AND logic. But I'm going to show you what's significantly different between the both of this. So we could represent this table as a graph right now. -1, 0, 1. So if X is 1 and Y is 1, so we have 0 here. And if X is 0 and Y is 0, we have 0 here. And if X is 1 and Y is 1, and Y is 0, then we have 1 here, and we also have 1 here. That's like representing these outputs in the graph. So if we represent these outputs in the graph, this is what we have. Now, can we separate this in its input space? The answer is no, because it forms like an X sign. So if we try to draw a line here, we see that 0 is here, but also 0 is here. So 0 is in one space. And because of that, we're not able to save the representation of XOR. Now, this proof here posed a significant roadblock for the development of the perceptron in the 1950s. And because the perceptron was, indicated as a failure because it wasn't able to solve this problem, until in the late 90s, another paper was written that talked about a process called backpropagation. And backpropagation it basically used a perceptron but as a neural network, so multiple perceptrons with a hidden layer and with gradient descent algorithms. And that's another paper that I will totally be discussing in my next episode. I really hope that this is something that you found helpful, and yeah, let me know if you found that helpful. Drop a comment, words of support, encouragement, whatever questions, and I'll be happy to answer it. Thank you.